In this lecture, we're going to look at how election is done in a couple of popular systems in industry. They are Google's Chubby system and the open source Apache ZooKeeper system. Both of these systems use consensus or consensus-like approaches to solve election. One approach to using consensus to solve election is to have each process propose a value. Everyone in the group reaches consensus on some process PI's value, and then PI is elected as a new leader. Whichever is the lucky process whose value is chosen as the consensus value, in fact becomes the lucky leader in the group. This is one approach. This is not necessarily the approach that these systems follow in industry. The systems in industry follow Paxos-like approaches for election. Paxos, as you've seen elsewhere in the course, is a consensus solving protocol. It's guaranteed to be safe, meaning that it assures that never is the case that different decisions are reached by different processes for the consensus variable, but it's only eventually live, which means that it doesn't guarantee that the protocol will ever terminate. Google's Chubby system uses a Paxos-like approach, and Apache ZooKeeper also uses a Paxos-like approach. So let's look at Google Chubby first. Google Chubby is a system for locking. It is an essential part of Google's internal stack of systems. Many of Google's storage systems, such as Bigtable and Megastore, rely on Google Chubby for locking and for writing small configuration files. Chubby maintains a small group of replica servers. For instance, a Chubby cell might contain 5 replica servers, server A, B, C, D, and E. And one of these servers is elected as a master server at all points of time. So at any point of time, exactly one of these servers must be the master or the leader, and all the other servers in the group must get to know about who the leader is. This is essentially our leader election problem. Right? So for instance, in this case, server D is the master here. Now, in order to make sure that there is exactly one master and everyone knows who the master is, an election protocol is required. Potential leader, a server that wants to be a master or a leader, tries to get votes from the other servers. Each server votes for at most one leader, and when a potential leader gets a majority of votes from the group, in this case a majority would be 3 or more of the servers voting for you, then that server becomes the new leader. When you have at least 3 votes from the group, you can become the leader. So why is this approach safe? Well, essentially every potential leader is trying to reach a quorum in the system. And once again, this is an example of a technique that you have seen elsewhere in the course that should be familiar to you. Quorum is essentially a majority or larger. Since any 2 quorums, no matter which processes they contain, are guaranteed to intersect in at least one process, and each process can vote for at most one leader, you cannot have the case that there are multiple leaders elected by this election protocol. So this algorithm guarantees safety. Why is this algorithm live? Well, it's only eventually live because, of course, you cannot solve consensus in an asynchronous system. And so failures may keep happening so that no leader is ever elected. But if things go right in the future, when messages are not delayed too much, when not too many bad failures happen, then the protocol has a good chance of converging and terminating. In fact, the folks at Google saw that elections typically take few seconds. That's a typical time to run an election. And the worst case that was noticed in the original paper written on Chubby by Google noticed that the worst case election run took only 30 seconds. Chubby also uses a concept known as leases. After an election finishes, meaning a leader has been elected, the other servers in the group, in this group over here, server A through E, guarantee that they will not run another election for a while. Okay, so this while of time, or this time duration, is called a master lease. This is the minimum amount of time that the master is guaranteed to be the leader. Okay, this is typically said to be a few seconds. The master lease must be renewed by the master by simply getting a majority again. So as long as it's able to get a majority, it can continue to be the leader without going through the overhead of running the entire leader election protocol all over again. This technique of leases or master leases also ensures that if the master fails to renew a lease, for instance, it has failed, or has just become very slow, then automatically the other servers start a new election run where a new master is going to be elected with a new quorum. Next, we're going to look at election in Apache ZooKeeper. Apache ZooKeeper is an open source system that is a centralized service for maintaining configuration information. ZooKeeper uses a variant of Paxos called ZAB or ZAB, which stands for ZooKeeper Atomic Broadcast. ZooKeeper needs to have a leader elected at all times. The way leader election works in ZooKeeper, at least the vanilla way of electing leaders in ZooKeeper, is by having each server create a new sequence number for itself. Let's call these sequence numbers as IDs. Essentially, each server does the following. It gets the highest ID so far. It fetches this from the ZooKeeper file system, creates a next higher ID, and it writes this into the ZooKeeper file system. At the end, whichever ID remains, the process that wrote it becomes the new leader. Okay, so the highest ID server becomes the new leader. So this ensures that as long as the files are written atomically, that files are overwritten completely, and you don't have partial writes from two different servers, you're ensured that there is exactly one ID in that ZooKeeper file at the end, and so everyone knows who the leader is by looking at that file, and the leader also knows who the leader is by looking at that file. Okay, so for instance, N80 might be elected as leader because it has the highest ID in the group. What about failures? Well, when you have failures such as the leader itself crashes, one option is for everyone to monitor the current master, for instance, by using a failure detector such as heart beating or ping-ponging. When there is a failure detected, the processes initiate a new election run. However, when the master fails, multiple other processes in the group might initiate elections simultaneously, and this may lead to a flood of messages. Even though you could use a way to suppress the election messages so that at most one of them completes, still it does lead to an explosion of messages. So the option that is actually implemented in ZooKeeper involves each process monitoring its next higher ID process. So N32, which is the second highest ID process in the system, monitors N80. N32 itself is monitored by N12, N12 is monitored by N6, and so on and so forth. And of course, N3 is monitored by N80 so that you wrap around the ring. If a process has a successor, that is the current leader in the group, this would be N32, whose successor is N80. And if that process successor has failed, then N32 can immediately become the new leader. So it doesn't even need to run a new election protocol. However, if your successor is not the leader, for instance N12 or N6, then you need to wait for a timeout and you need to check your successor again. So if you time out waiting for your successor to respond, then you make sure that you then point to your successor's successor. If your successor was the leader, then you can become the new leader. Now, conflicts may happen in the system because two different processes might write the same sequence number into ZooKeeper file, and might turn out that both of them think that they are the leader in the group. The leader might also fail during the election run. To address both these issues, ZooKeeper uses the two-phase commit protocol, which is run after the sequence ID protocol that we have discussed before. In this two-phase commit, the potential leader, which sees its own sequence number in the ZooKeeper file, sends a new leader message to all the processes in the group. Each process that receives a new leader message waits for a while. It might receive new leader messages from multiple prospective leaders. It responds back with at most one ACK message, with at most one vote message, and it sends it back to that potential leader that has the highest process ID. Now, what does the leader do? Well, the leader waits for a majority of processes to send it back ACKs. If it reaches a majority, then it knows that it is a leader because each process would have voted at most once. And if it's got a majority, if the leader has gotten a majority, then it's sure that no other potential leader would have gotten a majority. This is the same idea as quorums or majorities that we have seen elsewhere in the course. Once a leader has his majority of ACKs, it can then send a commit message to all saying that it is the new confirmed leader, and everyone else on receiving this commit message update their leader or elected variable to be the new leader. Okay, so this ensures that safety is still maintained because once a leader has a quorum, no one else can have a quorum, and so it becomes a new leader. However, this may not guarantee liveness. It's possible that two potential leaders that send out new leader messages simultaneously, maybe there are more than two leaders, suppose there are three leaders in the group that are sending out new leader messages, each of them gets about a third of the votes or third of the ACKs from the group, and so now no one has a majority, no one has 50% or more of the ACKs in the group, and so liveness is not guaranteed here. You may need to rerun the leader election protocol again. However, safety is guaranteed because of the use of quorums. So that concludes our discussion of election in Google Chubby and in ZooKeeper. Next, we'll discuss in the next lecture another classical algorithm called the bully algorithm.